So in this video, I'm going to solve some simple problems, and my target is to show you how to apply Newton's law of motion and get out relevant information such as the distance covered by the motion or some angle in order to keep the stability of a system, or the period of things flying, etc. So this section we are going to talk about the application of Newton's law on different dynamical systems. So let us first start with the Atwood machine, which is a machine like this. There is a big pulley right here which is hanging rigidly by a bar. It is supported here, and the pulley can rotate in both ways, either this way or that way. Alright, so it depends on the system or what you hang from it. And let's say hanging from it are two objects. Let us give it the name M1. So that's the mass M1, and there is another object which has the mass M2, and our assumption is M2 is greater than M1. We also assume that there is no friction, so no friction, whether this pulley is rotating based on its hinge or the center, or the interaction between the string and the pulley. So no string, mass 2 is greater than mass 1, so we know that mass 2 will be falling under the influence of gravity. Right, and number 3, as usual circumstance we accept for the string is massless and inextensible. Okay, so in this case we have to find out, let's say there is a distance here, so the distance where we have allowed the objects to fall, or the system to go on from a static to dynamic situation, and during that time the distance from the ground of the mass M2 was d, and so our question would be how much time does M2 require to cross the distance d. So the question is what is the required time? So this is our question. T to cross the distance, or rather, i.e. to fall across the height d. So that's the time. So let me write a time, and let us call this time capital T, and then with a subscript d. So Td equal to what? That would be our question. So here is the system once again, and we are required to apply Newton's law in order to answer our question. So this is what we're going to do. So step number 1, apply Newton's law for object number, let's say, M1. So remember, we have gravity working in vertically downward direction, and of course if the object starts to move, then it's going to be accelerating with a certain acceleration. It's time for us to see whether that acceleration is constant or not, but assume at the moment, at the instance when we are letting the system to go, then the acceleration that starts working would be a, and let's assume for simplicity it would be in the downward direction. But don't worry about it. If it's the other way around, the math will give us the answer. Okay, so if that is the case, we need to set up a coordinate system. So step 1, set up a coordinate system. So let us choose the coordinate system to be, this is a one-dimensional system if you really understand the situation. And so let the upward direction be y, or rather the positive y direction. I think you'd at this point would like to say that we should have taken this to be the negative y direction, because the downward direction should be the plus y direction. And I do agree. In that case, it would be less complicated and more intuitive. But this would show you that regardless of the choice of a coordinate system, as long as we are consistent, then this choice of plus direction and minus direction hardly matters. The point is we need to be consistent. So what do we have? We have the g, the gravity, acting as, in this coordinate system, negative g y hat. Okay, so that would be the gravity, and for our acceleration we would think that acceleration should be, so a should be negative, should be in such a way so that a vector would be minus a y hat. So that's how it should work, because we have assumed that m1 is, so this is because m1 is less than m2. That's what we have assumed. Now our second step is to apply Newton's law for mass 1. So step number 2, Newton's law for mass 1, m1. So how do I do that? Well, if the object is accelerating, so then m2 is going downward, that would mean that m1 would be going in the upward direction. So acceleration would be in the upward direction for m1. Okay, the gravity is bringing it downward, so this would be mg in the downward direction, and there would be tension along the string which has to be greater. So what do we have? We have T, which is positive, and then minus mg, which is negative, would be equal to, so this is the sum of all the forces, right? Sum of all the forces should be ma, so, or F net should be equal to ma. So this is F net, right? So this is going to be ma, and this m is going to be m1, because we are talking about mass 1. So notice that a is positive here and a is negative here. Okay, so that's the first step. So let's apply Newton's law for m2. So that would be our step 3, Newton's law for m2. Well, in this case, a is going to be negative, so we're going to have minus m2a. mg is going to be negative, so we have minus m2g, and of course the tension is going to be positive, so we have T. So the T has to be the same in all circumstances because this string is massless, and A has to be the same, acting the acceleration acting for or due to the forces would be the same because the string is inextensible. So we have our two equations. So this is equation number 1 and this is going to be equation number 2, and let us solve them to find out the acceleration. Now how do I find the acceleration? Well, that's our step 4. Solve 1 and 2. How do I solve them? Well, first you have m, so t from 1 would be equal to m1 times a plus g. Substitute that in 2. What do you find? mt equals m2 g minus a, but from 1 it should be equal to m1 a plus g. Alright, so since they are both t, they have to be equal, and can I solve them? I think I can. So I have to solve for a, right? So solve for a. So what do I get? I get m 2g minus m2a equals m1a plus m1g, m1g. Bring all the a's to the same side, so we have m1 plus m2 times a equal to, bring all the mg together. So what do we have? We have m2 minus m1 times g, and that allows us to solve for a. So we have a equals m2 minus m1 divided by m2 plus m1 times g. As you can see, this object in the parenthesis, which is a ratio of masses, does not have any units because the units cancel themselves, because you have the same type of quantity in the numerator and the denominator. And that allows us with dimension 1, because this object has no dimension, it's just purely a number. And so therefore we see that g has the unit of meter per second squared, and that's the same unit for acceleration, and all side checks out. And of course, as you can see, the acceleration is really a portion of g, but since this object here is constant, right, and is supposed to be less than 1, and this is also a constant, okay, we see that it's accelerating in the downward direction with less acceleration than the acceleration for gravity. So obviously a is less than g, and that is intuitive because you are constraining the system and redirecting acceleration, and of course because of the pulley, m1g and m2g are kind of working against each other, so you're reducing the acceleration. Now toward the final step, we see that the acceleration is constant, and we know how to deal with constant acceleration. So our last step, step 5, is, I believe it's step 5, right? Yeah, it's step 5. So that should be to find out the time. Now, we say the system started from rest. So the initial velocity is 0. Initial velocity is 0, right? And we know that our expression for time was going to be dictated by this relation, that delta y, or y minus y naught, is going to be v naught y times t plus half a t squared. Now, in our coordinate system, we say that this is the distance d, okay, and notice that this was the distance plus y. Alright, so if the top point is the initial point and if the bottom point is the final point, what do we have? We have y minus y naught, because y is going to be bigger, has to be less than 0. So in our case, this guy is going to be 0 and this guy is going to be m2 minus m1 divided by m2 plus m1 times g, okay, and this guy, if this is equal to d, well, it's not d because d is a positive quantity and y minus y naught needs to be negative, because y naught is the initial position and it is more in the direction of plus y, so it's going to be actually minus d, okay. And so for g you're going to have a minus sign as well, because it's actually opposing the direction of plus y. So in that sense, you actually balance everything, all the signs, and there is no problem. So m2 plus m1 times g, well, there is a half there, and you have td squared. So if that is the case, this is the required time. You have td equals, well, what is it equal to? Well, half goes there, so 2d divided by g, and then you have m1 plus m2 divided by m2 minus m1, and you are supposed to have a square root, and that is the required time, and that's also a problem.